Welcome to a special episode of Math for Game Development, where today we're going to talk about geometric algebra, which is an interesting area of mathematics that I've been studying recently. And I've been looking for applications in it to game development, which is what we do in this channel. And the reason that I think you'll find it interesting is because I've found a lot of great intuitions for understanding things like rotations in 3D math, and especially quaternions. Through the lens of geometric algebra, quaternions are intuitive and much easier to understand. And my promise to you is that by the end of this video, quaternions will make simple and intuitive sense to you. I mean, quaternions are a notoriously difficult part of game development, and geometric algebra simplifies them such that they'll be just clear as day for you. In fact, they're going to make so much sense that when we start talking about quaternions, you're not even going to realize that we're talking about quaternions, but you're still going to understand everything, and then you're going to go like, whoa, that's a quaternion. It's going to blow your mind, I promise. I promise. So that's a big promise, and in return, I want you to make a promise to me that you are going to watch this video on normal speed. Not double speed, not 1.5, not 1.25. I see you trying to do that 1.25. Flip it back to 1. And the reason is that learning happens at the speed of writing. I want you to take the time to watch what I'm writing and think about what I'm saying at normal speed. If you speed it up, then it may go too fast for you to pick up what I'm putting down. So let's talk a minute about the prerequisites of this video. I'd like you to have a fair grounding of the basics of linear algebra before we get started here. Just what is a vector, have a good handle on what that is, dot product, cross product, just the very basics. And I'm going to go over a few things as review. If they seem alien to you, then you should go to the other parts of my channel and watch the videos on vectors, and that will get you up to speed. Let's just talk about them real quick. What's the dot product? It is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. The big thing to take away from dot product is that when two vectors are facing in a similar direction, their dot product is a big positive number. When they're orthogonal or perpendicular, the dot product is 0. And when they're facing in opposite directions, it becomes a negative number. So the dot product is kind of a measure of how similar two vectors are. Same thing with a cross product. Cross product is a product where the magnitude of it is the magnitude of A, magnitude of B times the sine of A and B. And the cross product gets largest when the two vectors of the product are orthogonal to each other. So a cross product is kind of like a measure of how dissimilar two vectors are. And the last thing I want to review is the definition of a projection. A projection onto B of a vector A looks like this. It's an orthogonal projection. This part right here is the projection. It's like casting a shadow from A onto B. And in linear algebra, we know that this projection is defined as B dot A over B dot B times B. Again, if this looks unfamiliar to you, then you can review all of this in the other videos on my channel. I suggest you go do that review real quick until this is all solid for you, and then we'll continue. Okay, so there's one more prerequisite, a concept that I've not covered on my channel before in linear algebra, called linear independence. And so I want to talk about that before we move on to the next thing. Suppose you have this big bucket of vectors, x0, x1, so on. And then we have a new vector, xk, that we want to compare against all of the vectors in our set, in our big bucket. So the question is, can I write this formula? A0 x0 plus A1 x1 plus yada 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 equals xk. So here's what I'm doing here. I'm taking a weighted sum of all of the vectors in the set. I'm saying take this vector, multiply it by some real number. Take that vector, multiply it by another real number. Is it possible to take all these vectors and then multiply them by some numbers and get xk? So I'll give you an example where it is possible, where it's not possible. Let's say we have these two vectors right here. Here's x naught, and here's x1, and then here's going to be xk. And I think you can see that if we make x naught just a little bit longer, so if we multiply it by like 1.5, and then if we make x1 just a little bit longer, maybe we also multiply it by 1.5, then we can sum the two together and get xk. So in this case, we have these two vectors are linearly dependent. Okay. Now let's look at another example. Let's use these same two vectors, x naught, x1. But let's say xk is a vector that comes out of your screen, which I'm going to denote with this little symbol, a circle with a dot in it. Suppose it's coming right out of your screen into your eye. In this case, you can tell that you're never going to take a sum of x naught and x1, no matter how long you make them or short you make them. You're never going to get anything that comes in or out of your screen. It's just not possible. You can get to any point on your screen, but you can't get anything that comes out of your screen. So xk is said to be linearly independent of the other set of vectors. Okay, and that concept is important. We're going to run to it in just a little bit. Okay, let's get started with the actual geometric algebra. Suppose I have two vectors, A and B. Okay, I'm going to create a new product. Like dot product or cross product, it's a way of multiplying two vectors together, A times B. But this time it's going to be A wedge B. And the product is called the wedge product. Okay, A wedge B. Now what do you get when you do A wedge B? With dot product, when you do A dot B, you would get a real number. With cross product, you do A cross B, you would get a vector. But with a wedge product, we don't get either of those. We get something new called a bivector. I'm going to call this bivector X. And you can think of a bivector as sort of like a plane. It has an orientation, and the plane is going to have both the vectors A and B in it. So when you do A wedge B, you get a bivector that contains A and B. Okay? Now, bivectors follow the same rules as vectors do. You can do scalar multiplication. You can do addition. A bivector has a magnitude and an orientation. In this case, the orientation of the bivector X is the orientation of the plane that contains both A and B. The magnitude of the bivector X depends on the magnitudes of A and B and the relationship, the angle between A and B. If you take a bivector, X, which is kind of like a plane, and you multiply it by 2, let me actually make something that might actually be twice as big here. You get another bivector, which is twice as large. If you add two bivectors together, you get another bivector that might actually have a different orientation than your original two bivectors. All of this should sound very familiar because vectors work the exact same way. Now, the first time you might see a bivector, it might be confusing, so I want to spend a little bit more time exploring exactly what a bivector really is. And I want to do so by analogy with a vector. If you think of a line, then pick another color here, then a vector is kind of part of that line. You can think of a vector as part of a line, okay? This vector A is just some section of this line. It's not the whole line, it's just a section of it. By analogy, if you have an infinite plane here, which I'll represent with this box, the bivector is not the whole plane, it's just some part of the plane. Here's my bivector x. So it inherits its orientation from the plane in the same way that the vector inherits its orientation from the line. But it also has a magnitude. It encompasses some finite area of that plane, and that's the magnitude of the bivector. The units of the vector are going to be, the vector has only one direction, it goes along the one line, so the units of the vector are a length. But the units of the bivector are an area. The magnitude of the bivector is an area. So let's return to wedge product. There's another way that I want us to think about wedge product. If I have this vector A and this vector B, and I want to do A wedge B, okay, then I want you to think about this wedge as an extrusion. We're taking A and we're extruding it out along B. We're taking A and we're sweeping it out along B. And the result is that I get this area right here that is a bivector. A wedge B is a bivector. The reason it's useful to think of it as an extrusion is because we don't have to stop here. We can go crazy. There's no reason we can't do A wedge B wedge C. Let's say that this right here is our vector C. So what's happening is we're going to take this bivector A wedge B and we're going to sweep it up. We're going to extrude it up until we get a box. And this is called a trivector. We had a bivector before, and now we had a trivector. Now I want to ask another question, and that question is, what is this? A wedge A. If I take a vector A and I wedge it with itself, well, then I extrude it with itself, and it would just turn out to be kind of a smushed line like this, okay? But remember that a bivector is a part of a plane. The rule is that it always has to be a plane, and it always has to have an area. You can't take a wedge of a vector and a vector and get a vector. You're always going to take a wedge of a vector and get a bivector. And since the resulting bivector after this wedge, when you extrude it out along its own line, the area of that is going to be 0. And so this result, A wedge A, equals 0. It's kind of surprising. A vector wedged with itself should equal 0. But if you think of it as being sort of like cross product, when you take cross product of a vector with itself, you get 0. What about if I already have some bivector, here's my bivector, and I wedge it again by B? Well, this is the same thing as saying as doing this B wedge B first, and the answer to that will be 0. So if I do a bivector wedged with a vector that's in the bivector, that's in the plane of the bivector, then that wedge product will be 0. So we're starting to see some kind of rule here. If I have just an arbitrary list of vectors that I've wedged them all together, that will be 0 if the vectors have a certain relationship with each other. And that relationship is why we talked about linear independence at the beginning of the video. If the vectors are all linearly independent of each other, then the product of all these wedges will not be 0. But as soon as one of the vectors is linearly dependent on the others, then the wedge product will be 0. Incidentally, that means that any product of more than 3 vectors in 3 dimensions has to be 0, because you can only have 3 linearly independent vectors in 3 dimensions. But anyway, let's continue. So there's one other thing I want to talk about with wedge product before we move on. If we have A wedge B, how does that relate to B wedge A? What's the relationship between these things? Well, I want you to think of it in analogy to cross product. If you have A cross B, you'll get a vector that points one way. And if you have B cross A, you'll get a vector that points the opposite direction. So with wedge product, same thing is going to go on. And the way you can think of it as is, when you do A wedge B, you get a plane that has an orientation. It faces one direction. Then when you do B wedge A, you get a plane that has the flip orientation, like the normal vector is facing in the opposite direction. The two planes share all the same points, but one is facing up and the other is facing down. Okay. So now let's move on to the next big idea in geometric algebra, and that is the contraction product. Okay. And to understand what the contraction product is, let's actually go back to the wedge product for a moment. Remember that if you have A wedge B, then you get this bivector X. A wedge B is X. I want you to think, for starters, of the contraction product as being like the opposite of the wedge product. Okay? So if we have X, and we contract out one of the vectors that we use to get X, okay, then we undo that extrusion and we get the original vector. Remember, we took A and B and wedged them together to get X. So now contraction product takes out one of those vectors and leaves you with only the remaining one. And let's see what that picture looks like. Here are the two factors of X, of A contract X. Let's write A like this. Okay, here's A. And you can imagine if A's got a little hook on the front and on the back, and it hooks into X, and then it shrinks itself out of existence. Okay? Sort of like this. X becomes a little thinner, and then a little thinner, and then finally just becomes a line again. The vector B comes a little thinner. See, A kind of shrinks itself out of existence, and then the only part of X that remains is the part that is perpendicular to A. So that's the way I want you to think of contraction product. It's sort of the opposite of wedge product. So let's try that again with another example so that we can kind of see what's going on here. This time we're going to ignore how we got X in the first place. And I'm going to draw a completely arbitrary vector inside of X. But we're still going to do the contraction product. We still want to know what A contract X is. So let's do that in slow motion again. Okay. In the end, we get a vector. Here's the original A. We're going to get a vector that is perpendicular to the A, but still resides within the plane of X. Okay? So that's contraction product. Now, contraction product has a nice property. If I do A contract B, and A and B are both vectors, then that becomes the same as A dot product B. So contraction product is like a generalization of dot product in higher dimensions. And I'll do one more example. Let's say that we have a trivector, which, as we saw before, is what happens when you extrude, when you wedge product 3 times instead of just twice. So we have like an A wedge B wedge C sort of situation here. And we are going to contract that by a bivector. Okay? So here is Y, and here is X. And we're going to figure out what X contract Y is. So it's the same as before. Same rule as before. X contract Y will give us the part of Y that is perpendicular to everything in X. So let's see what that looks like. I'm going to simplify this by taking out some of the vectors of X. All right. Remember, X can be expressed, because it's a bivector, as the wedge of 2 other vectors. So I'm going to break the X apart into, let's call them A and B, and we'll say that A wedge B equals X. So this is going to be the same as if we take Y and we contract it by A, and then we contract it again by B. So we take Y, we contract it by A, and then we contract it again by B. Same thing. And so let's see what that picture will get us. First, let's contract it by A, and we'll get a bivector. Remember, our Y trivector is a volume, and it will squish along this vector A, and when it squishes, you'll get just this bivector right here that is perpendicular to A. So we still have B, and now we're going to squish along B, and we're going to get this right here. And this right here is the result, X contract Y. Okay? That's contraction product. Now it's time to look at the most important product in geometric algebra, and it is called, unsurprisingly, the geometric product. And it is a way of multiplying 2 vectors together that is so important, it doesn't even have a symbol. There's no dot or crowd. There's nothing here. You just put the vectors next to each other as if you were multiplying A times B. And the geometric product of 2 vectors is defined as A contract B plus A wedge B. But we're not just limited to multiplying 2 vectors together with the geometric product. We can multiply any 2 geometric algebra objects. So let's try it with multiplying A times the bivector B. It's the same thing. A contract B plus A wedge B. Definition of geometric product gets more complicated in other cases, but this is the only definition that we're going to need for this particular video. So remember at the very beginning where I talked about dot product as being sort of a measure of how similar the two vectors are. And we've seen that this guy right here is kind of a generalization of the dot product. The contraction product you can think of as how similar the vectors A and B, or the vector A and the bivector B, are. And wedge product, I think you probably have seen by now how it is similar to the cross product, although it's a bit more general and useful. And the cross product was a measure of how dissimilar two vectors are. And so here in the geometric product, you've got everything. You've got all of the information about the relationship between A and B. You have the similarness part and the dissimilarness part. That's really what the geometric product is. It doesn't have a strong geometric intuition other than that it contains the entire relationship between these two vectors. And that's incredibly useful for us. We're going to exploit the geometric product to do a lot of cool things. So you may be confused at this part because you're looking at this sum right here and you're thinking, how can we add the result of a contraction to the result of a wedge? Contraction, after all, is this contraction for two vectors is equal to A dot B, which is a real number. And this wedge product is a bivector. And how do you add a real number to a bivector? That doesn't really make any sense. So the way we're going to think about it is, let's remember complex numbers. Here's a complex number for you, A plus BI. And if you look at the plus in this case, it's really not doing anything. You cannot add a real number to an imaginary number. So when we deal with complex numbers, we just say this is exactly how simple it can get. We can't do any more addition here. We also sometimes think of complex numbers as a vector, which has the real part and the imaginary part. The real part and the imaginary part. So the plus in this case is just notational. We're not adding anything together other than in the sense of that they're sitting next to each other. They're both components in a larger space. And in geometric algebra, it's the same way. This expression is, you're not actually doing any adding here. You're just grouping them into a vector. And this vector, the same way that the complex number has a real part and an imaginary part, this vector has a scalar part, A contract B. It has a vector part, but in this case the vector part is 0 because there's no vector in this sum. And then it has a bivector part, A contract B. That's the bivector part. And then it has a trivector part, and then it may have many other parts. Although in 3 dimensions, we'll just stop with the trivector part. Okay? So it's okay to add a vector and a scalar together, for example. If I have this vector v and a scalar 5, this is an okay thing to do. It just works out to think of it as like a supervector. In fact, it has a name, a multivector, that contains 5 as the scalar part and v as the vector part, and 0 as all the other parts. So let's get some practice in with the geometric product by discovering that the geometric product has a special property meaning that being that everything that you can multiply under the geometric product has a unique inverse. And that means that if we take A, there's always a unique B that you can multiply by A so that you get 1 as the answer. Now, dot product and cross product and other things, they have inverses, but they're not always unique. Wedge product and contraction product are the same way. But with geometric product, your answer is always going to be unique, and so we're going to discover what this is. So in this case, we're trying to find B. B will be the inverse of A if A times B equals 1. So we're going to calculate what this inverse is. We're going to try to solve for B. So let's first expand using our definition of geometric product. And then we're going to simplify because we know that A contract B is the same as A dot B. Okay? So this is what we have right now. A dot B plus A wedge B has to equal to 1. Now, we know that A wedge B is a bivector, and there's no bivector part in 1. So A wedge B has to be equal to 0. So that means that we have A dot B is equal to 1. That's what we know so far. Now, since A wedge B equals 0, that means A and B have to be linearly dependent on another. And since there are only 2 vectors involved, that means that A has to be a scalar multiple of B. Okay? So we know that A, let me write it this way. B is a scalar multiple of A, where K is some real number. Okay? So I'm going to take this, and I'm going to plop it in here, and I'm going to get that A dot product of K times A equals 1. Now let's solve for K, and you're going to see that K is equal to 1 over A dot A. Now I'm going to take this and plop it back in there, and we're going to see that B equals 1 over A dot A times A. So this is the inverse of A. Every vector has a unique inverse, and we've just calculated it what it is. It is in fact a scalar multiple of itself. In this case, the scalar we're going to multiply is 1 over A dot A. So that's pretty cool. And another way to indicate notationally that we're going to multiply by the inverse is we can do like this. These two are going to be the same thing. Okay? So I'll bet you never realized that you can divide 2 vectors. It's true, you can in geometric algebra. B divided by A is the same thing as the geometric product of B and the inverse of A. So notice that we have an interesting property here. That means that if the length of A is 1, then A times the inverse of A, then A equals the inverse of A. A and the inverse of A are the same thing if the length of A is 1. All right, so that was some pretty good practice. Hopefully it solidifies a little bit for you what the geometric product is. So now we have all the geometric algebra tools under our belt, and we can start drilling towards my promise, which was that we're going to understand quaternions by the end here. So the first step to get there is to remember what is the definition of the projection of x onto A. So here's my picture. Here's A. Here's x. I'm going to do an orthogonal projection of x onto A, and the result will be this vector right here, the projection onto A of x. And the definition of that from regular old linear algebra is x dot A over A dot A times A. Now, let's use the things that we learned so far from geometric algebra to express this in a more geometric algebra way. So, x dot A over A dot A times A, I'm just going to reorganize here. I'm going to say x dot A times 1 over A dot A times A. I just took this A dot A from the denominator of this fraction and I moved it out to its own thing so that you can see that this right here looks like A inverse. So let's simplify a little bit and write it again like so. And now, remember that x dot A because these two are vectors, is the same thing as x contract A, and A inverse I'm going to write as over A. So this is x contract A times the inverse of A, or divided by A. So this is how you write projections in the language of geometric algebra. X contract A over A. And in fact, this formula works no matter what A is. It could be a vector, it could be a bivector, it could be a trivector. So I'm just going to use that as the geometric algebra definition of projection. If you want to project X onto any object, be it vector, bivector, trivector, or whatever else, you use this formula. X contract A over A. Pretty cool. All right, and there's one other useful thing we can do if we have X. Here's X. And we project it onto A. We get the projection here. But what about this vector? This is called the rejection. The rejection onto A of X. And it is defined as the vector such that the projection onto A of X plus the rejection onto A of X equals X. Okay? So if you take X and you project it onto A, then the rejection is like the information that you lost. If you add it back to the projection, you get the original vector again. So let's see what the rejection is in the language of geometric algebra. The rejection is going to be, I'm just going to subtract projection from both sides, x minus projection. And let's replace that with the definition that we came up with just now, which was x contract A over A. And now I'm going to do a stupid trick here. Okay? I claim that X is equal to X times A over A. Because A over A is 1. A divided by itself is 1, and X times 1 is just X. So I haven't really done anything over here, but I'm going to take this and I'm going to substitute it in right here. And so we'll get X times A over A minus X contract A over A equals the rejection. All right? Now you're going to have to take my word for it that the geometric product is distributive. And I have a multiplication of A inverse at the end of both of these terms. So that means that I can undistribute, like reverse the distribute that I just did. Okay. And I get that right there. Okay. And now I'm going to apply the geometric product to that guy right there. I'm going to expand that geometric product. And let's see what it gets us. This will be x contract A plus x. Man, I always write A when I mean to write x. Minus x contract A again, divided by A. These two right here come from that, and then this comes from here. All right. And now we see that we have an x contract A minus x contract A. So that goes away, and we get the result x wedge A over A. This is equal to the rejection onto A of x, written in the geometric algebra tools that we have. Okay? So let's do just a double check right here, just so that we can see that we're saying the projection plus the rejection should equal x, because that's the way that we defined it. The projection, recall, is x contract A over A, and the rejection is plus the rejection is x wedge A over A. You see how there's a nice symmetry here. So let's try and simplify this. We're gonna do a distribution rule here over A. And then you can see that this is a geometric product right here. So I'm just gonna undo that geometric product. And now I'm going to do an associative rule, and A over A is 1, and so sure enough we get just x. Pretty cool. So let's move on. So the next step is, here's a vector A and here's a vector x. We want to find the reflection around A of x. If A is a mirror, and we take x and we reflect it around A as if it were a mirror, then we would get a reflection here. And that's what we want to find. Trust me, this is gonna get to quaternions. Now, this is useful even if you don't care about quaternions, to understand the geometric algebra way of doing reflections, because reflections are used all over the place in game development. But we are gonna get to quaternions, so hang on tight. We want to know the reflection, and the tools we have are the projection and the rejection. And recall that the projection plus the rejection equals the original vector x. Well, should be pretty clear to see that the projection minus the rejection is the reflection. Projection minus rejection, that gives you the reflection. So I'm going to define the reflection around A of x as the projection minus the reflection, minus the rejection. Now, let's continue to write these in the geometric algebra definitions that we just established before. So the projection was x contract A over A, minus the rejection was x wedge A over A. Now I'm going to apply a distributive rule, and we'll get x wedge A minus x contract A minus x wedge A over A. Same distributive rule as we applied before. Now I'm going to do two things at once. First of all, recall that x contract A because x and a are both vectors, is equivalent to x dot a. The next thing I'm going to do is, you see how x and a, so recall we had this rule where x wedge a is the same thing as negative a wedge x. So I'm going to write plus a wedge x. Okay, so we had negative x wedge a is the same thing as a wedge x over a. Okay. Now one last step I'm going to do here. Dot product is commutative, so I can swap a and x here. X dot a is the same thing as a dot x. I lied, that wasn't the last thing. Let's continue. Again, because both of these are vectors, a dot x is the same thing as a contract x. So I'm just applying the same rule as I did before, but in reverse. Over a. And then finally we see that this is the definition of a geometric product right here of a and x. So the geometric product ax is equal to a contract x plus a wedge x over a. Now notationally, ax over a is the same thing as ax times a inverse, and we arrive at something called, for obvious reasons, the sandwich product. All right, if you didn't get every step of all of that manipulation, it's not a huge deal. It might help if you review the video and see if you can come up with all of these steps yourself, because then you'll really have learned it. But for the first pass, I really just want you to understand that we started with this definition of reflection, and we did a bunch of manipulation, and we got to something that looks like a sandwich product. So that means that a sandwich product is a reflection. Okay? When you do a sandwich product like this, when you see a sandwich product, you're looking at a reflection. If you want to reflect a vector x around a vector a, just sandwich that a and the a inverse around it, and then you'll get your reflection. So now it's time to finally talk about rotations. We're here. We can use reflections to construct a rotation. If that sounds surprising to you, then think about what this pair of mirrors does to this point right here. Here's our x, okay? First, we are going to reflect it along this mirror, and then we're going to reflect it again around the other mirror. And you can see that it's been flipped twice. It got reflected twice. So it got flipped, and then it got flipped again, or in other words, it got unflipped. So it's no longer flipped, but yet it's in a completely different place. Our point has been rotated around the mirrors. Okay, this is like when you go into the department store and you're trying on clothes, and they have those special mirrors that are at odd angles. And if you look in the right place and you raise your hand, then your reflection will raise its right hand. You know, normally if you just look in your bathroom mirror, you raise your right hand, the reflection raises its left hand because it's been flipped. But in these special mirrors in the department store, if you raise your right hand, the person in the mirror will raise their own right hand. But they're still facing you because they've been rotated 180 degrees around. So that's what we're trying to get here. We're trying to take two reflections and put them together to get a rotation. Okay? So let's see what that looks like. If I have this vector x and a vector a, first let's reflect x around a. Okay? And then let's do a vector b right here. And once again, we're going to reflect x around B. So you can see that there's some kind of rotation, there's some kind of angle, we'll call it theta, between A and B. Okay? If you're at A and you want to rotate over to B, then you're going to rotate theta degrees. And the same thing seems to have happened with X. X has rotated, but you can see it's rotated much more than theta. In fact, it has rotated 2 theta. This angle right here, this angle right there, is 2 theta. So that's really interesting. If you have 2 vectors that are theta degrees apart, and you reflect through the first vector, and then you reflect again through the second vector, you will get a rotation, and that rotation will be 2 theta. Okay, the vector that you reflected twice will have rotated in the same manner as the original vectors, except it's gone twice as far. It's done twice the rotation as before. That means that if you want to rotate something by theta degrees, then you need to start with 2 vectors, A and B, that are theta over 2 degrees apart in rotation. Then when you do so, you'll have this vector x. It'll be reflected once, it'll be reflected again, and you'll see theta over 2 degrees of rotation in that vector after you've rotated it. Okay? So what we've learned is that 2 reflections make a rotation, and that rotation will be double of the rotation of the 2 vectors. I hope that made sense. So let's write this out algebraically. Okay? We have x, and we're going to rotate it around A. We're going to reflect it around A using our sandwich product, which, as you know, does a reflection. And then we're going to take the result of that reflection, and we're going to reflect it again around B. So let's see what we got here. B inverse A, x. Sorry, there's not supposed to be an inverse here. I don't know why I wrote that. BA x A inverse B inverse is a rotation of 2 theta degrees of x. Okay? And I'm going to skip a bunch of manipulation here because manipulation is boring. But I claim that this is the same thing as B over A x B over A inverse. Okay? If you want an exercise, I recommend that you try this at home. Figure out how to get from this step to this step. All right? So it turns out if we take x and we sandwich product x by B over A, then we get a rotation. So what is B over A? Let's see what it is. Well, B over A is clearly B times A inverse, which is a geometric product. So recall that A inverse is 1 over A times A dot A. Okay, so B over A is equal to 1 over A dot A times the geometric product of B and A. And you can recall that that has 2 parts. I'm going to expand the definition of geometric algebra here, and we're going to get B contract A plus B wedge A. Okay? So this part right here is a scalar, and this part right here is a bivector. Remember how I drew bivector earlier in the video? It's like a plane. So this thing, B over A, has a scalar part and a bivector part. If you're familiar with quaternions, that should sound familiar to you. okay? But I'm not going to call it a quaternion. I'm going to call it a rotor. A rotor. In geometric algebra, this is called a rotor. A rotor is a rotation by double reflection. And one more review. If the rotation between vectors A and B is theta over 2, then when you use this rotor as a sandwich product, like that right there, then you will get a rotation of theta. Now, as I said before, this is really similar to a quaternion. So let's look at the way a quaternion is constructed. So now, if you've never seen a quaternion before, you can actually stop watching at this point. You've learned a rotor is, for all intents and purposes, a quaternion. You understand everything that you need to know. But I would like to continue and examine the comparison between rotors and quaternions and convince you that they really are exactly the same thing. Okay? If you understand rotors, if you understood everything up to this point in the video, then you totally understand quaternions. So let's review what is a quaternion. A quaternion has a vector part and a scalar part. Okay? Let's say you have a vector v. This is a unit length vector, so I'm going to give it a little hat. And a theta, an angle through which you want to rotate your whatever it is you're rotating, your vector. Okay? Then the way to construct a quaternion is with this formula. V hat cosine theta over 2. Sorry, V hat sine theta over 2 cosine theta over 2. This right here is the vector part. And this right here is the scalar part of the quaternion. If you've watched my videos on quaternion, then you'll recognize this theta over 2, and I justified it by talking about rotations in the fourth dimension, and forget all that. If you understand the previous part of this video, then you know where this theta over 2 is coming from. It's because when you use two vectors to rotate another vector, you end up with double the rotation, and so you have to start with theta over 2. That's it. Don't worry about the interpretation of a quaternion that it's a four-dimensional object and that. Forget about that. Quaternion is just a rotor. It's a rotation by double reflection. Okay? Now, I came up with a formula for a rotor before, and we're going to make sure that these are actually the same thing. Okay? So it looked something like this plus B wedge A. Remember that this plus is the same thing as like having a group of two things. So this quaternion has a vector part and a scalar part, and this rotor has a scalar part and a vector part. So they're the same, and a bivector part. So obviously the scalar part here corresponds to the scalar part there. But what about this? This is a vector part and this is a bivector part. Well, every bivector has a corresponding vector. It's called the dual. In the same way that every plane has a normal. Okay? So every bivector has a vector that's perpendicular to it. So if you have this quaternion, you can figure out what the bivector is. There's going to be one unique bivector that has the same magnitude as this vector. So hopefully you can see that the bivector here is similar to the vector there. They contain the same information. Here, the vector of the quaternion tells you the axis of rotation of the quaternion. But here, the bivector of the rotor tells you the plane of rotation. Okay, so any vectors in that plane will rotate such that they remain inside the plane. And this 1 over a dot a is a normalization factor. It's not here in quaternions because quaternions are assumed to be unit length. But with rotors, you can actually, they can be any magnitude and the calculations still work. But if you assume that the rotor is of unit magnitude, then it's identical to the quaternion. So one more thing I want to note here. When you're building a rotor, or a quaternion, okay, and you want a rotation that goes from A to B, and you're going to choose A and B such that they are theta over 2 degrees apart, you end up getting B over A, whereas you would think that you would get A over B, but A over B is wrong. The rotor that rotates from A to B is B over A. So why is that? And the intuition you can think of to remember this is that when you have a point A and a point B, and you want the vector that points from A to B, then what do? You don't do A minus B, you do B minus A. You start at B and you subtract A and you get the vector that points from A to B. Same thing if you want a rotation from A to B, you do B over A. This division is analogous to this subtraction. And that's the end of this video. I'm going to continue to study geometric algebra and try and share any interesting results that I get with you here on this channel. Hopefully you understood everything about rotors and quaternions and wedge product and contraction product and reflections and projections. And if you have any questions, please ask in the comment below and I'll try and clarify anything I missed in the video. See you next time.